Hey there, I'm Deep Dhillon and welcome to your AI injection. Today we have Emil Winebrand joining us. Emil is the founder and CEO of insoundz, a generative AI audio enhancement company focusing on using AI to remove unwanted noise and output studio-grade audio. Emil, maybe get us started by, walking us through like what problem are you trying to solve at insoundz? And maybe I like to start with what do people who don't use your product do to sort of face the problem?
Yeah, that's a good question. So as you know, audio is everywhere. Specifically, we're on an podcast. It's the way you interact with people. It's the way you interact with your loved ones, your car, your devices, and it's how you do your work and so forth. But it doesn't get the right attention all the time. And audio, it has always been a second brother of the video. The problem is that to create a high quality audio and really a high quality production, it takes huge efforts that people are seldom aware of. And why is that important? If you take, for example, a nice study that was done on academia, it's been shown that when you have bad audio in terms of quality, lost packets, whatever, people tend to think that the speaker is less intelligent, less likable, his topic is not interesting. And in communications, that's kind of audio quality is the main complaint that people have. That's like 50 to 60% of complaints is about audio quality. So it's important and it takes a lot of effort. What do people do today is either use professional services like audio engineering, audio editors, if that's in content creation. And in live, they basically use whatever is out there that can be any sort of algorithms for live audio enhancement, but really none of them create the right experience. So it's still bad, that if that makes sense.
Yeah, and I think, this problem's probably gotten bigger in many ways in the last few years. Like if we think of like COVID's always an interesting kind of temporal demarcation, right? Pre-COVID, if you were doing any kind of professional content production, you'd spend a lot of time and energy making sure that you have the right mics, the right, people are in the same room, you have sound engineers, really making sure that the raw audio with which the post-production team is going to work with is, of high quality.
Yeah.
And then, as soon as COVID hit, one of the things that struck me was like, really, really big shows, like Trevor Noah and other folks, they're like in their apartment cutting these like huge shows that, a few days before were done with a lot more kind of like hardware up front. And to fast forward to today, people realized a lot of those efficiencies. Like, like our podcast, you're in Tel Aviv. I'm actually in Spain right now. We're having this conversation, across a low budget, if you will, a medium Zoom. The output quality can be a struggle to get it to sound decent. Like in our case, we had some problems with audio for a while and we think we've resolved them and gotten them a lot better sounding, but we're certainly not as good as if we have like super high quality mics and we're in the same spot and all of that. So it seems like you'd have no shortage of potential clients.
It's a good, very good point. So it starts from communications like we're having now. Typically, communication is tiered by environment, compression, bandwidth, lots of stuff, but then goes to high quality content production. And there is a huge, much increased awareness of the actual content. As you say, post pandemic, people begin to consume more content from home, work more from home, being more efficient on one end, but then people are getting more aware of the quality of content they're consuming, especially as it affects their energy levels to a sense, because if you're having a bad conversation for a long time, basically you're drained, you're energetically drained. And there's actually a biological, physiological reason for that. Your brain works 10 times harder to compensate for bad audio. You actually physically feel that you're drained. And it actually comes from, wasting your energy reserves on processing.
Yeah. And I'm sure a lot of us have felt this, like, and there's different types of extra attention that one has to employ to like figure out what somebody's saying, right? There's the part where if all the audio was perfectly clear, you still have the language overhead that your brain is going through. And then your mind's also like teasing out the audio, the ideas, sorry. But what you're kind of getting at is just the problems with understanding the actual words being said and the burden that that puts to like listen more closely. Like if you're at a party and there's a lot of other conversations going on, we've all felt that added energy of having to strain and like really pay attention to somebody just to figure out what their words are. So I think you're sort of suggesting some milder version of that. One thing I want to do for our listeners, because a lot of folks maybe don't understand why it's hard to clean up a crappy audio file. And I think before we get into, just why this is such a wonderful application of AI and machine learning, if you can help set the stage for somebody who maybe hasn't taken a bunch of signal processing classes and really tried to sort of understand the complexity of what happens inside of an audio signal to make it very difficult to separate, to basically get back to the equivalent of a green screen in imagery, to get to a point where you have something unadulterated, not affected by filters, so then you can, go apply filters or whatever.
Yeah, a very complex question. I would start by blaming, first of all, our ears. We are so much sensitive to audio than to visual. Just to give you an example, in visual, we have 3 types of color receptors, frequencies. Right? Everybody knows that. And there's also, the dark mode without color. In our ear, we have a huge spectrum. For each kind of spectrum portion, we have different follicles in our ears that actually sense that. We have so much sensors, so many intricate details that your ear is able to extract, which makes any type of processing really very hard. Our sensitivity is too big. And by the way, typically hearing and listening to something is considered more ground truth than seeing something. You believe your ears much faster and with higher reliability than you believe your eyes.
That's kind of interesting. I mean, there must be some kind of evolutionary reason for that. I think in the modern era, we put audio last, right? Like we get great AI models for language first, and then everybody talks about imagery and vision, but virtually nobody's really talking about on the audio side. And it's been like that for 40, 50 years. It seems like at least in the tech world, that we think of it as later. But I'm sure if you go to Hollywood, it's a totally different answer. Like when they talk about audio as being essential, it's at the front. So I'm wondering, is there some biological reason for why we trust our ears more than our eyes?
First of all, predator, danger detection, anything that happens in your environment comes first from the ears. Actually, your ears cover 360 while your eyes cover a 120 degrees angle. So it's kind of your radar. And by the way, your ears draw the attention of your eyes and not the other way around. It's very hard to fool our ears because, that's a survival mechanism. If you're walking in a dark forest and you hear something, you better be alert. Otherwise we wouldn't be talking here. So I believe that there is a biological reason for that. And then it kind of evolved from that. People mainly communicate between themselves, and most of our information before the written word was actually audio, right? People were just speaking one to each other, one to another, etc., etc. And I think our bandwidth perception, the amount of information we're able to pass to each other, actually increased with time and with the enlargement of brains of Homo sapiens. But that's going too far, maybe. And it kind of evolved from that, I think. And language, written, especially written word, stuff like that came much, much later. So it's not biologically fundamental. And vision, although you perceive a lot of information from vision, but you were unable to actually store and tell any data using visual signs up until maybe last 30,000 years, when they started drawing stuff.
Yeah, that's a really good point. It was audio, like storytelling, and
that's your information storage.
Or maybe sticks in the mud or something for a little bit, but that resolution is so much lower than audio. Huh, interesting. So then if we fast forward a little bit, let's say to 5 years and before, there's a lot of audio signal processing reasons why it's hard to go from a bad audio signal to a green screen equivalent. And maybe you can walk us through some of those as well.
Yeah. So, as I said, maybe just earlier, that our ears are sensitive to very small and intricate features in the audio. So, to create real green screen, you need to cover a lot of details. And if they're not consistent, not concise, and if there's a discontinuity, if anything is going wrong, your ear will be able to hear that to a level that you can have a perfect signal, but even if you have some disturbance that is by a factor of 100 smaller than the rest of the signal, but it's in a certain frequency area where where your ear is not saturated, you will still hear it. You don't have that in images. Like pretty much, if that's the background level, pretty much everything else is at the same level. Your eyes are unable to separate such a big dynamic range features, if that makes sense. But let's get to what does it mean to perceive speech? Okay, so somebody is talking from some distance, from you, from a microphone, doesn't matter. So let's assume his speech is perfectly generated by his mouth, throat, etc. And then it goes through some propagation medium, which is air, bounces back off walls, floors, whatever. And already when the audio comes to, let's say, a microphone, it's already distorted in some way. On top of that, you have environment noise that is added to this. So you begin kind of masking some of these important features in the audio by overlaying that with environment noise. And then you have potentially microphone noise and some microphone effects and whatever. And then you also have the medium where the audio is transmitted. Does compression, maybe some pre-processing in order for it to better fit the bandwidth pipeline. All of these kind of incur additional difference from the original signal. When you get to the point that you need to reconstruct the audio, so you can actually clean up quite nicely with, classical signal processing. You can just remove kind of the deteriorated components of the audio, whether that's frequencies, whether that's time instances. You can remove them, you can ignore them. But then your audio becomes very, narrow, shallow, and it's just missing a lot of components. So now what can you do? In previous technologies, you didn't have a lot to do. Today, you can regenerate those components. For example, missing frequencies. For example, correcting for reverberations. For example, adding some dynamic range and dynamic depth of the frequencies range. So you actually mix the residual audio with a regenerated one, and the result is incredible. It really
that's interesting. So that sort of suggests that you're doing. Are you doing some kind of pre-filtering before, and you're, because it seems like there's a couple of approaches. Like one approach you could take is you could try to get the generative model to truly learn the filter transformation of all these effects that you itemized, like, the channel effect, the room, etc. And then, but what you're saying here is a little different. It's making me think maybe you're bandpass filtering or something, and getting down to the raw speech, and then reconstructing the character of the room effects and the other things that would be a lot harder to sort of represent into a filtered itself. Is that right? Am I hearing you right? Or
it's a mix of the things. First of all, even if you can characterize some of the room effects and it doesn't mean that they're invertible in that sense that you can reconstruct the original sound. Basically, if you multiply something by 0, you cannot extract the original value.
Mm-hmm.
So the other thing, additive noise, if it becomes much stronger than some audio component in that frequency space, that component just gets lost. It's impossible pretty much to extract it. So typically, what they used to do in classical signal processing, just discard it. But here, so not everything. What I'm trying to say is not everything is invertible. And by the way, most of the things are non-invertible. Most of these, hard disturbances are non-invertible. So the real way to
I mean, largely, like,
compensate for that.
just a quick side note, is that largely because, let's take a highly reverberant hall like Carnegie Hall or something. A lot of those effects that you're perceiving are higher frequency contributions that are very noise-like, right? Like they're very like stochastic and random appearing. So it doesn't necessarily make sense to have a filter that can get rid of it and put it back. Is that kind of what you're getting at?
Yeah, I would though say that first, like lower frequencies get scrambled first. You just end up with a lot of high frequencies, and they're not kind of sporadic. But everything on the low end and the things that we perceive that we correlate with intelligibility and quality, they really get lost first, and they're really sporadic. And some components do get preserved, but a lot of it gets lost. So yeah.
Have a ton of data, don't know where to start? Chat with one of our principal data scientists at xionyx.com. That's XYONIX.com. You'll talk to an expert, not a salesperson.
So maybe let's take a little bit of a turn. And I think these two topics will kind of align as we go, but maybe walk us through, like, what are you training on? Like, what's the training data? Is it, and what does it mean to define a green screen audio? Like, are you actually putting somebody in a pristine recording environment and getting a true, green screen version of the audio? And then also maybe taking that cleansed version and passing it through a bunch of, known common effects? Or are you, taking an existing bad sounding audio signal? And I would think you're doing something like the former, at least for the maybe supervised fine tuning in the end, but for the original unstructured tuning, maybe you're doing something more unstructured. Yeah. Yeah. Like more like sort of like we do with like images or something, like where we're training on known omitted parts of the signal or something.
All of the above. However, I want to take you to potentially even one step further, if I can.
Sure.
So our company, we don't see ourselves as just kind of creating one model for cleaning. Different businesses, different enterprises really look for different things in audio. Even in the same market segment, different companies want to differentiate themselves by offering something a little different. Let me share an example. We have one platform on board that really wants to remove ums that people say during podcasts, while you really want it as part of, like typical human communication, like in communication, office type of communication platforms. So different requirements. You still can call this one clean and this one great audio. And sometimes customers say they want to remove music. Some customers want to keep the music. So you really want to specify, because we're a B2B company, we're looking for a clear specification for the customer, how to bring value to his business. So we've built a machine actually that can take that type of specification and create a data set from it. For now, we started off with just having a catalog data. A lot of the data is our own. The green screen, as you call it, is people and actors that we hired for long periods of time to create high quality data. We recorded them in studios. And then we kind of use that data to go through different types of transformations, which in audio, they're called room impulse responses. By the way, we acquired a huge number of those room impulse responses. We had a team that did a lot of recordings and a lot of noises and a lot of cataloging. So we have that kind of structure of data.
I'm going to just chime in really quick on that. Just for our listeners that maybe don't know, there's this sort of cool phenomenon in audio analysis. Like, so if you walk into a room and you take a hammer and like just whack it on something hard, it'll create, what we call is an impulse, and it sends a pressure wave all the way through the room, and it starts bouncing all over the room. And then if you record that thing, you can now recreate the essence of that room. And that's what Emil's kind of referring to. And not literally with a hammer, but like that's the way I think of it.
That's one way.
Yeah. Could be literally a hammer.
So basically you kind of recreate those different environments, as you mentioned, with pulse responses. Then you add some physical augmentation on that, which can be a moving head, rotating head first. So it creates a lot of, dynamic changes of that room impulse response. You can have Doppler effect, Doppler shift, because somebody is moving in the room. A lot of those physics has to go into the training pipeline. Then you add on top of that. Please.
I was just going to say this is really interesting because we've talked about on the podcast in the past generating training data from physics, and it seems like this is a perfect example because in essence what you're trying to do here is you're trying to recreate the ability to take any one of these sort of pristine audio recordings that you have of your voice actors and put it through basically like any room that could exist in the real world or an alternate world. Apply any random filters that somebody might get if they're like munging it through GarageBand or doing, sticking it through hundreds of different guitar effects, pedals, or voice effects. Like you're trying to recreate the ability to make all of that. And then once you have all of that, and you're mentioning Doppler, which is an interesting one. I don't know, somebody's out there recording while somebody drives by or, but it speaks to an intriguing idea of creating a very leveraging a known and maybe finite set of physics phenomenon, but then expressing that ability to then go take these pristine signals and munge them up into all kinds of permutations that ideally represents everything you would see out on the internet today or something.
And you don't have to represent everything. You need to represent everything that the specific line, the use cases that specific line tries to achieve. It's very important, I think, to limit that scope, because otherwise you're solving a lot of problems and not really becoming an expert in a specific problem. I'll touch on that in a second. Now, I want to take this whole idea that we just talked about, munging everything, into the next level, which is we are currently at, is that we decided instead of having a catalog data set that you need queries to kind of pick up the right sounds and mix everything together, we decided to take that to the level of Gen AI. So basically, you specify to the Gen AI, to a Gen AI that generates audio that was trained on all of that data. What do you want it to output? So you actually augment in a much larger scale everything that goes out of that data set. So if that makes sense, let me reiterate that. So imagine that you have, male speaker, one female speaker, and that's all your data set. Okay. With today's Gen AI, you can draw a line between that speaker and the male and the female speaker, and you can get all the spectrum of potential speakers that can represent them. So you want to enjoy that while training, an AI to do some task, creating an input for that into that pipeline that is much wider in that sense.
What's going through my head is I'm trying to figure out how you actually train up this model. And so I'm envisioning you have two time series signals that are aligned. One with the person in the green screen, the perfect recording, and then you have one with whatever effects you've applied. And now you back up, and the model that you're training is for any given sort of sequence of, I don't know if you're doing this in time series, but but what I'm imagining is that you've got a sequence of values in time, like if for our audience, you've got that temporal signal that we've all seen a million times. And now you have to predict the next value of that time series signal. But instead of going to your noisy thing, you're going to go to the pristine one, and that's the value you want to predict. And similarly, you're going to be able to make this, and you might go out, n values in the future, but that's sort of the essence of the training that's going to help your model learn that really complicated transformation that you're applying. Am I on Mars with that, or is that in the ballpark? And maybe link that up to the point you were making before.
Yeah, it's kind of the other side of the whole training pipeline. let's touch on that. So yeah, basically you're trying to create from the noisy part, you're trying to create the clean part, the clean signal as the clean time series as mentioned. Now, it's not done in purely in time domain because the task is too difficult to really recreate that, time domain signal. But luckily, our ear is more responsive to frequency domain or some kind of mix between mixed frequency and time domain. So you really define the way you're trying to approximate the clean signal from the noisy one in that time frequency space. What I was getting beforehand is how do you create the data for that training? That was my reference beforehand. So it's not only comes from catalog data sets. It's everything that's also between, but maybe we'll touch on
okay.
later.
So let's go back to the time series and sort of frequency world that you're operating in. Can you give us a little more color on what that means? Like, why can't we just work in the time domain, and what problems actually come up? Why can't we just directly predict? Is it because when the model that we're sort of evolving tries to predict future sequences, that some of the errors are, I don't know, glitchy or something? Like what ends up happening there?
Yeah, let's just take it for one thing for granted, perhaps, that you can never predict the exact signal. There will be always a mistake, always an error. Now, how do you control that error? Is perhaps there's a way to conceal it in such a way that our ears are less sensitive to that. So when you're trying to approximate in time domain, it's very hard to do. And there are a lot of kind of sporadic zigzags that you get around the signal. And this is something that is very audible to our ear. In some cases, they call it musical noise. And these are noises that are really, really, annoying our ear.
Yeah.
And the perception is bad, really bad quality. If you're trying to do that, perhaps like to approximate the signal and like have a residual noise, but make it inaudible. Let's say, for example, maybe for audience that is not aware about a lot about frequency domain, there are two components. There's a way to look at frequency domain in two components, that magnitude and phase. So our ears are much more sensitive to magnitude change rather than phase change. So potentially you would rather to have most of your errors in the phase domain rather than magnitude domain. That's one way to look at it. In time domain, in time series, you don't have that, kind of way to conceal that clearly, how to conceal these errors so it won't be audible to human ear.
Yeah, that makes a lot of sense. It's kind of like, maybe for the audience's benefit, like if we think about like MP3 or MP4, the modern compression algorithms kind of leverage a psychological concept that humans, I think it's like 1/3 of the power of like if you're looking at a particular note, let's say like, a 440 hertz signal, like a concert A tone, if you're hearing a tone that's just a little bit like 1/3 or less as strong as that tone, but slightly more or less hertz, like 441 hertz or 439 hertz, the vast majority of us can't really hear that difference. And basically what you're saying is if you can squish those errors either into the phase part or the spectral part, the frequency domain, then you can sort of take advantage of that, in essence, that limit in our physiological response.
Yeah, you're spot on. We actually use those magnitude masks, they call them in MP3, to conceal some of the magnitude errors below them. And then you can focus your AI to really, really recreate the stuff, really be accurate where it's audible, and just, throw away everything that is not important below kind of spread the problems below hearing threshold. Same goes for time domain. There is another interesting psychological effect that if you have like a high amplitude audio for post that time, there is some masking time. That means some of your follicles are saturated, so they can't hear for, 20 or 100 milliseconds after that, anything. So push some noise there, push some inaccuracies there. So there are a lot of effects that you can use. And by the way, AI does that much nicer, much more efficient than classical MP3s and stuff like that, because you can really specify how to do this.
Well, I mean, it's fascinating how you've approached this problem, because you have in essence, I mean, a near infinite training data set, right? You can give it a bajillion different permutations. Yeah. So you really have a lot of audio to work with. The question I would have is, do you find that you miss stuff like that? Is there any examples of like big types of problems that you maybe didn't have represented in your training data that you needed to go back and find and somehow include?
Yeah. Well, great example I can give you is, for example, you have a speech and there is standing ovation after a speech. So is the standing ovation where people shouting and clapping, is that considered noise, or is that part of the content?
That's hard.
So yeah. By the way, that kind of ties the loop to for customers to really understand what they need, and we help them understand what they need before we generate that. We create that model for them. So yeah, we had also with a high pitch barking dogs. That was a crazy one. So one customer, another key, typically toddlers crying in the background is something that's considered unpleasant and people want to remove it in professional settings. But in some of content creation, you want that. That may be part of the media. Not everything considered noise in all cases, and not everything considered good and relevant is relevant in all cases. So that's typically we have to do 1 or 2 iterations to really cover 95% of the needs for a customer.
Have data, have a hypothesis on some high value insights that, if extracted automatically, could transform your business. Not sure how to proceed? Bounce your ideas off one of our data scientists with a free consult. Reach out at zyonics.com. You'll talk to an expert, not a salesperson.
Cool. Well, I could probably nerd out with you all day on the super deep technical stuff. So let's let's take a shift here and jump out a bit. Tell us, maybe walk us through, like, who are the customers that are really that you're really kind of doubling down on, that you think, hey, this is the use case that's the one that's really gonna take insoundz to the next level? Or are you going kind of like, are you focusing more on these sort of consumer apps like the Zoom kind of context, or are you going down into a particular podcasting kind of scenario, or maybe you're going to like a particular part of Hollywood trying to reduce costs? Like, how are you thinking about it from the business standpoint, and what kinds of customers are really attracted to insoundz?
Yeah, good question. So mainly software platforms that do audio processing in their pipeline. We're trying to actually use the flexibility that Gen AI brings in order to really attend a wide cross-industry markets. So half of our market is communications, and that means Zoom-like, but not a B2C play. Rather, even Zoom, have their own kind of B2B. I think most of the revenue even comes from B2B. So that's where high quality audio really is, people are willing to pay extra for that. So we have communications, we have content creation, and that content creation can be from podcast, musicians, singers, and all the way up to Hollywood level productions.
Well, so you're not just doing spoken word, you're doing music applications as well.
I specifically focus on singing. So human voice. Human voice is the center of everything. We're not doing instruments and stuff like that. We can separate them as a background channel. This is something that we do, like as part of the specification that these enterprises give us. On the third kind of angle, we're going to post-production tools, mainly in automated post-production that is done in the cloud rather than, DAWs and plugins and stuff like that. The SaaS platform we're building right now has some manual work in it. So we meet a customer, get the specification, create a pipeline out of it, generate a model, give the model to the customer, he's happy, deployed, etc. This whole process is about to be automated, fully automated. So customer can log into our website, specify via text exactly what he wants, get a model deployed on the cloud. He can drag and drop and try. He can tune it. He can say, no, you know what? I want to remove dogs as well. He can actually fine tune that model, listen, and then decide that it's now ready to deploy. And then he can just pull it and deploy it as a cloud container in his product. So we're really, really trying to cover industry-wide solution here, not just focusing on one thing or the other. And the reason we can do that is because we think we uncovered and understood the mechanics of taking audio needs into an AI model.
I mean, that's an interesting thing. It sort of implies that a lot of your users require customization. And I wouldn't have guessed that. I would have guessed that like you would have maybe a handful or 10, 15 different types of application, like one being extract voice, get to the green screen equivalent of voice with in any kind of podcasting environment. But you're sort of suggesting that people are more particular than that. I don't know, almost like that wouldn't be enough to go wide. But I'm having a hard time wrap my head around that. It seems to me like if we just take this podcasting app scenario, it seems like that alone should be one model.
Mainly, yes, but platforms, businesses that serve this area want to differentiate itself. They want to differentiate themselves from other customers by actually giving different capabilities, like removing ums. I don't want to go into too many details because it may give out secret phrase of customers that we're engaged with. But you're right, podcasting is more kind of a fixed format. But a lot of the other stuff really require customization. I want to perhaps take an analogy into image processing. Like let's take the problem of segmentation. So it's, segmentation, a lot of open source, a lot of companies worked on it. Pretty much everybody in the AI space knows what is image segmentation. But when you take it to real business applications, and this is where the difference between, kind of a wide scale to a B2B product. When you want your image segmentation program to work, let's say for driving cars in a specific parking lot, you would really have to tune that to that parking lot. Otherwise, like the 80% performance is not good enough. So you really need to make sure you're tailored to the use case. I'm taking it back to communications. Let's say we have a communication company, let's say Zoom, I don't know, maybe smaller, second tier, third tier, doesn't matter. They have their own processing pipeline. They have their own restrictions. They have their own compressions and stuff like that. Compressions add artifacts. They have their own bandwidth restrictions. They have their different working sets. We actually just take those requirements and tune that into the model. And then you have optimal performance for this customer. If you train it for a different type of compression, audio compression, okay, you can train it wide, but you won't really get that level of performance. And this is where the B2B difference comes into light.
Cool. I'm going to ask you a question that I ask a lot. So a lot of our listeners are product managers or folks who are like trying to figure out how do I use, AI and machine learning in my company, in my products. Can you maybe, for somebody who's not used to just thinking about machine learning and AI, can you offer some advice on like what they can do to even understand what's possible with respect to their product and how they might be able to get started thinking about how to integrate machine learning or AI into their products?
That's a very interesting question. First of all, at least for me, I'm looking at AI as a very sophisticated tool to solve a problem. So you really start from the problem, not from from like looking how to put AI just in a business, because otherwise that's going to be very hard. I think really to understand what AI is capable of is kind of, for me, thinking about what a human employee can do.
Yeah. And
that pretty much puts a limit, give or take, on what is the capability of an AI machine. So, the AI machine won't be able to launch into space, right? But it can potentially take some burden off of the mundane tasks, or even not so mundane tasks that some of your employees do, and create efficiency there. Also, I would look for structure. If there is a clear structure to the task, or I would say some kind of rules that you can think of, even if they're vague, but you can think of set of rules that can describe that task, you can probably get an AI to do that, or at least assist with that. So that's the way I would suggest approaching that.
I think that's very sage advice. Well, Emil, thanks so much for coming on the show. I've got one last question for you. If we fast forward, let's say 5 or 10 years out, and everything you're working on and envisioning working on, works out, maybe walk us through how the world's different for those of us on the outside of your company.
Everything, all your audio interactions everything that you do with audio will be calm, will always feel as if you're in listening to a high quality podcast rather than rushing and enjoying and having all the noises around you. And most importantly, audio should be safe because we inherently trust our ears so much more than our eyes that audio has to be safe. And this is also something that insoundz is really deeply involved into. We are trying to think how audio is going to be used in 10 years. And still we're going to trust our ears and not trust and not be intimidated by fake audio.
That's I look forward to the day when I don't have the harsh. I think that's part of Zoom fatigue, frankly. What you're describing, is people are on their headphones, they're watching, and that audio gets kind of harsh. I think it's part of the fatigue. That's a great picture. Hopefully, we're all going to live more serene lives when you're successful. So, thanks so much for coming on the show, Emil. It's been great having you. That's all for this episode of your AI Injection. As always, thank you so much for tuning in. If you enjoyed this episode and want to know more about implementing AI in your company, you can try chatting with our bot, Zybo. Just Google Zyonix Zybo. That's XYONIX, and Zybo is XYBO. Also, please feel free to tell your friends about us, give us a review, and check out our past episodes at podcast.zyonix.com.